This is VLSI data conversion circuits, lecture 50. Today we will begin the study of another important piece of the delta sigma loop, and use this as an excuse to study D to A converters. Alright, so we will be looking at this animal. Now, as the name suggests, the input is a digital code, the output is either voltage or current or charge. All right. And if one plots the digital code on the x axis and the analog output on the y axis, you get, ideally you are supposed to get a characteristic like this. Please note that these inputs actually do not make any sense, the code can only be an integer, right, and delta is called the step size, just like in a to D converter, just as the positions of the x and y axes are interchanged, and this represents a 3-bit D to A converter. Delta is the LSB or step size of the DAC. Now, just like how the thresholds of an A to D converter can be in error due to various factors, for instance due to mismatch, in an analogous manner the steps of a D to A converter can also be in error. So, how do you think an erroneous characteristic will look like? Will it be changes in the x axis or in the y axis? Only in the y axis. So, the common kinds of errors are very similar to what we discussed with the A to D case, right. If one joins the output levels of an ideal D to A converter, you must get a straight line. In practice, one common kind of error is when you join these points, you get a straight line. However, this straight line is shifted up or down from the ideal line, and this is called the offset. Okay. Another kind of error, again all this should be very familiar given you are exposed to A to D converters, is when you join these points, you get a straight line. However, the slope is not delta for every change in the input code, it is more than the delta that has been quoted for example on the data sheet. So, this is like having a larger delta, that is all. Okay. So, this is called gain error. Does it make sense? Okay. So, gain and offset errors are not really that problematic in a system, because both of these will be calibrated out anyway. Okay. What is important is that the straight line remains a straight line. Of course, that is not true either. So, the outputs may be deviating from their ideal values in this fashion, all right. And therefore, as you can see, the step size is not the same from code to code, and therefore, the step size at code n, if we call the output for code n as V n and the output for code n minus 1 as V n minus 1, then this is the or rather the step size of code n is nothing but V n plus 1 minus V n, all right, and ideally should be delta. In practice, it is not delta, it is either larger or smaller. So, how can you quantify the deviation from the ideal step size? We know that they all should be about delta, and we are actually interested in the deviation from delta. So, analogous to the A to D converter case, the deviation from the ideal step size. So, that is V n plus 1 minus V n minus delta, which has absolute units of in this particular case volts, right. If you want to talk about compare different converters, it makes sense to not talk about the absolute deviation, but the relative deviation, in which case you normalize it to the step size, and this is called the DNL at code n. All right. And similarly, so this is normalized to the step size. The units are DNL of n is in LSB. On the other hand, the absolute deviation from the ideal output is also of interest, and that is simply is V n minus n delta, and again it does not make sense to talk about absolute deviation as a dimension quantity, right. So, you normalize this, and this is called the integral nonlinearity or INL of n. Okay. And the running sum of the DNL is the INL, just like in ADCs. All right. Now, these in practice it is not as if the converter will have just offset or just gain error or only DNL or INL, right. The whole thing will come as a cocktail. So, in practice the converter will have offset plus gain error plus nonlinearity, which is characterized by DNL and INL. So, if you want to find the DNL and INL of a converter, what should you do first? So, the way of finding DNL and INL is first remove offset and gain error, and then so by best fit, for example, and then from this you will find the actual the true LSB size, okay, which will result in a closest fit to the D2A converter characteristic. And once you remove offset and gain error, you can find the DNL and INL with the step size obtained from step 1, the LSB obtained from does make sense. The next thing is dynamic performance. The input to the D2A converter is a sequence, okay, and its discrete time Fourier transform is nothing but e to the x of n e to the minus j omega n sum over right. So, this is nothing but x of e to the j omega. Now, conceptually what the D2A converter is doing is taking the sequence of discrete time impulses, right, and converting it into a continuous time signal, all right, and therefore, one can think of the whole operation as replacing the discrete time impulse with a Dirac delta pulse, and the spectrum therefore of the continuous time signal is nothing but x of n. This is the sampling rate of the D2A converter, e to the minus j 2 pi f times f T s times n, correct. This is the Fourier transform of the continuous time signal. Does it make sense? Okay. So, how would you relate the discrete time Fourier transform to the continuous time Fourier transform? All that you need to do is replace omega by uh, 2 pi f times T s, all right. So, as usual omega equal to pi corresponds to f s by 2 okay, and therefore, if the discrete time spectrum look like this, and sorry, the discrete time spectrum looked like then all that one needs to do is to change the axis to 0 Fs by 2 Fs right. Unfortunately, generating Dirac delta pulses is not realistic in practice. So, every DAC has got a pulse shape, and we have discussed this before in the context of a delta sigma modulator. Common pulse shapes are the NRZ pulse, where the output can be thought of as x of n, in the time domain can be thought of as x of n times p of t minus k times T s, the output in continuous time is this, where p of t is 1 from 0 to T s, all right. So, can you comment on the spectrum now? So, you can think of this as taking the continuous time waveform, which is a sequence of Dirac impulses, and passing them through a low pass filter whose impulse response is rectangular. If the impulse response is rectangular, it follows that the Fourier transform is a sinc function, and it has null set multiples of 1 by T s, which is F s. Okay. So, in other words, the spectrum of the NRZ DAC will be something like this. Okay. On the other hand, if you had the so called return to 0 pulse, what happens to the spectrum now? So, for an NRZ pulse, the filter is of the form T s sinc f times T s. So, this has null set multiples of one by T s. For a return to 0 pulse, it is 2 T s by 2 sinc f times T s by 2, which is the same as T s sinc of f T s by 2, which means this has null set at at even multiples of 1 by Ts. Okay. And that makes physical sense. So, the spectrum for the NRZ, so this is the NRZ filter, if you like. The RZ filter will only have will look like that. Okay. So, these are often called the images of the signal, right, and as you can see, the images are attenuated to a much larger degree by a when you have a NRZ DAC pulse shape rather than a return to 0 DAC pulse shape. All right. And that makes sense, because a return to 0 pulse shape has got much larger transitions, and these transitions occur twice every period. You understand? That means that the jumps going up and down are much larger in the return to 0 case, which also means that it must have much higher strengths of high frequency components. So, the spectrum actually makes sense. So, now the question is, why would anybody choose a return to 0 DAC pulse, given that there is the signal has got lot more high frequency content. Do you understand? When you use an NRZ DAC pulse shape, the signal has got the images are attenuated to a larger degree. Okay. The height of the pulse is smaller, and there are no transitions in the middle. So, one obvious question that could be asked is, if everything is so nice about the NRZ pulse, why even talk about a RZ DAC? Okay. Yet we have gone and seen the applications of this in a continuous time delta sigma loop, right. We even discussed jitter and such. So, the question is, yeah, so why do you think a return to 0 pulse makes any sense at all? Pardon? Well, in the context of a delta sigma loop, as he points out, definitely, a return to 0 pulse has got is a lot, when you use a return to 0 DAC, you are a lot less sensitive to excess loop delay, right. But there is another important and not so obvious point that I will make now. No real NRZ or RZ DAC will have perfectly sharp edges, right. So, there will always be a finite rise time and a finite fall time. Now, let us consider a sequence, say 1, 1, 1, 0, 0, 0, right. Let us assume that it was 0 throughout. Okay. Now, an NRZ DAC waveform ideally would look like this. All right. And now, the rise and fall times A are not 0 first of all, and B they could be asymmetric. This is also a very common thing. For example, if you use a if you look at a CMOS inverter, for example, the rise time is always, if you not size the devices properly, you will find that there is always a difference between the rise and fall times. Okay. So, it is not uncommon to have NRZ DAC pulses where the NRZ pulse has different rise and fall times. I am going to grossly exaggerate the rise and fall time asymmetry now, and therefore, the actual waveform looks like this. Okay. Now, let me consider another waveform, another sequence which is 0, 1, 0, 1, 0, 1, 0, and with rise time and fall time asymmetry, the waveform would look like this. All right. Now, if the system is perfectly linear, consider this: the input sequence to the system is 3 ones followed by 3 zeros, correct, all right, and here it is 1 0 1 0 1 0. So, if the system is perfectly linear, since both these sequences have the same average values, is that something that you agree with? The average value of 1 1 1 0 0 0 is the same as the average value of 1 0 1 0 1 0, correct. So, if the DAC is perfectly linear, then the average value of the red waveform here should be the same as the average value of the red waveform drawn below, correct. Now, can you comment on the average values of the two waveforms? Pardon? The average value of the lower one is higher, and why is that?
Fall time is more.
Correct. Yes.
Area in this portion will be compensated by this.
Absolutely.
Here the fall time is much higher.
Correct.
So you have for every rise time and fall time you have some delta extra error adding.
Correct. So, it is a very good observation that if the rise and fall times were exactly equal, then when you compute the average, the loss in area here would be compensated exactly by the area increase there, correct. However, because the rise and fall times are not the same, these areas are not compensated. So, if you have more falling edges and rising edge pairs, okay, in a given amount of time, you keep accumulating that error, right. In other words, the average value of these two waveforms are not the same, and I mean this is an example I chose, but you can clearly see that even the average value of the waveforms depends on the sequence that is being put in. So, two sequences having the same average do not result in two waveforms with the same average, correct. So, what is this? Can you give me one word to characterize this property? It is nonlinear. You understand? Is this clear? All right. Let me put that down here. Two sequences with the same average value result in waveforms with different averages, and this is non-linearity. And this is all that is needed to establish that rise and fall time asymmetry causes non-linearity. Of course, to characterize this very carefully, I mean you can do it, but the bottom line is that using an NRZ DAC pulse shape with rise and fall time asymmetry will result in non-linearity. Right. On the other hand, with a return to 0 pulse, the height of the pulse must be twice, the duration should be half, and even if there is significant rise and fall time asymmetry, so whether it is 1 0 whether it is a 1010 pulse or a 11100 pulse, I mean whether it is a 1010 sequence or a 111000 sequence, we see that the average remains the same, right. It is just that the pulse shape, which was ideally a rectangle of height 2 and duration Ts by 2, is now altered, right. All that it means is that it is a linear phenomenon where the filter applied to the ideal impulse train is not what you thought it was, it is slightly different, which means that the high frequency response changes a little bit, but this is not a nonlinear phenomenon. Does it make sense? So, this waveform can still be represented as x of n to p of t minus NTS. Instead of having P NRZ, P RZ, it is some P hat RZ, that is all. Ideally, you would have expected this. Now, instead of having the blue pulse, you have the red pulse, but it is still a linear system. Okay. So, an RZ DAC is immune to rise time, fall time asymmetry. all right. Unfortunately, a return to 0 DAC has other issues, namely in the context of a delta sigma modulator, it has got problems with respect to jitter, as well as the loop filter now has to handle signals which are, I mean, whose peak amplitudes are twice when compared to the NRG case. Okay. But we see that the return to 0 DAC has an advantage over a NRG DAC. This becomes particularly important when you are running this at very high speeds, where the rise time becomes a non-negligible fraction of a entire clock period, or in cases where the precision required is so high that even a small change in the rise and fall time, or rather a small mismatch in the rise and fall time, can give rise to components which are significant when considering the very low distortion that one needs. Okay. So, in oversampled converters, we also saw the example of a third pulse shape, which is again fairly commonly used, and that is the exponentially decaying pulse shape. All right. Now, one way of implementing these DACs, let us just first consider a simple NRG DAC. The output of the flash is a digital code, and one can think of many ways of converting this digital code into an analog output, right. So, what is the simplest way you can think of converting? So, the easiest thing you can think of perhaps is a resistor string. You have a reference, you have a bunch of nominally identical resistors, okay, and you have some kind of mux. This is an analog mux now, which has many inputs, and the digital the digital code selects which one of these taps get to the output. All right. So, what do you think are the problems with this approach? Pardon? Of course, like okay, resistor mismatch, will mean that the steps are not exactly equal. All right. Can you comment on what do you call the monotonicity of this DAC? Pardon? It is monotonic. This is inherently monotonic. All right. Can you comment on the output impedance of this DAC? As you can see, depending on the digital code, right, the output impedance is this resistance in parallel with the resistance below. So, the output impedance is code dependent. All right. So, this can be, I mean, a big problem. From a point of view of non-linearity. I mean, the output waveform therefore will have different time constants depending on the input code. So, if you are interested in the entire waveform or the spectrum of the waveform, right, you should be prepared to accept a lot of distortion simply because the time constants keep changing depending on the code. However, if you are only interested in the settled value, right, then you do not need to bother, you only have to worry about the static aspects of the entire DAC, which is the resistor mismatch, right. So, the fact that the resistor output impedance is code dependent means that there is poor dynamic performance, right. Can you comment about the complexity of the decoder?
Everybody to increase.
I mean, how many wires must come from the DAC, from the resistor string to the mux? Pardon? 2 to the power n lines must come from the resistor string into the array, and all these switches must come together at one single node, namely the output node. Okay. So, you can see that this you are picking up a whole lot of parasitic, all right, okay, and therefore, this decoding logic, messy decoding logic and band limiting at the output node. Okay. So, all these problems basically have relegated this DAC to places where you really do not need either much speed or any dynamic performance at all, basically that is what it means. Okay. The nice thing about this is that it is inherently monotonic, all right, and the fact that the decoding logic is messy is also a problem. Okay. So, you use it in places where the logic does not get too messy, in other words where the resolutions are not very high and when you are not really interested in dynamic performance. Okay. Can you explain, I mean, can you tell me where you have seen this being used in the past? In a flash A to D converter, that is basically what you are doing, right. A resistor string is also, if you think about it in another light, you can think of it as a DAC where all the outputs are available simultaneously and you pick which one you want, right, that is what the mux is doing, correct. So, when you had a flash array where all the references were needed at once, right. This seems like a natural choice, right, that this resistor string has got all DAC outputs available at once, and all these are going to the comparator, offset, I mean whatever capacitors which store the reference, all right. And in that particular design example I discussed, where we needed only one reference at a time, all that you need to do is have an arrangement like this, and this mux figures out which of the taps of the ladder to pick and give to the that particular comparator. So, that is basically a DAC in disguise, you understand. That is a resistor string DAC. Again, because you have a lot of time for auto zeroing and so on, the settling time of the DAC is not really a big issue, and the fact that it is inherently monotonic is advantageous, all right. So, only in such applications you use a resistor string, a full resistor string DAC. Okay. So, in the next class we will discuss other topologies and see what their limitations are and what one can do about it. The fact that mismatch is a problem is it is not as if you magically get away from it, all right. Mismatch will always be a problem regardless of what DAC topology you choose, okay. All right.